very nice opportunity to be with you and to share with you what we do in other places in the region. And this first talk, I want to tell you about an ecological system in the Patagonian forest that we have been studying from different perspectives. One of these perspectives is that of seed propagation. I won't go into all of the details, but instead I will tell you a kind of reasoning that is typical of a physicist, and I hope that you will enjoy it. And the seed propagator is this animal. It is an interesting animal by itself. It is the only extant representative of a whole order, the Microbiotheria order. It is a very small marsupial. It is actually more similar to marsupials in Australia than the other marsupials in South America. Its common name is Monito del Monte, which I hope all of you understand. Although it is not a primate, it is a marsupial. They live here in the temperate Patagonian forest, which is this beautiful landscape where we spend as much of our time as we can, as you may imagine. They feed from the fruits of the quintral, which is this parasite plant. Is there a pointer? There's one here. Quintral is this plant. It's a parasite. It's a mistletoe. The monitos play a very important role in the ecology of the system because of a strong mutualistic relationship with this plant. They eat the fruits, and while walking along the branches of the hosts of the plant, as you can see here, they deposit the seeds. And the plant, being a parasite, needs their seeds to be deposited on appropriate hosts, otherwise they will not propagate. So there is a mutualistic relationship between these two species. And some of the seeds germinate very fast, like now I have two devices. This is the change. This is the last spot here, and it's already germinating. It is very fast. Here I try to convey this role that this species play in the forest. The monitos are the only dispersers of the quintral, which blossoms in winter. In winter, you can see the flowers of the quintral in the middle of the snow. And with flowers in winter, they are the only winter resource of the major pollinator of the forest, which is this hummingbird, the ruby hummingbird. Sorry. So the three species work together as architects of the forest, and they are of great interest to ecologists. So this project we had with collaborators in the ecology laboratory in Bariloche had produced a number of results and spin-offs. My favorite is this one, which is the emergence of a finite home range in a model of a forager that consumes a renewable resource, but it is not the one that I'm going to tell you today. Today it will be just the propagation of seeds. So we are trying to describe a system of seeds dispersed by animals. Let me try to formulate the problem in terms of the following three populations of seeds. First, we have immobile seeds, seeds in plants, this red density here. Then we have seeds inside the animals that are the ones that move. And we have the seeds germinating and eventually producing plants that produce new seeds, so they go here in plants. So these are just deposited in the substrate, and eventually they turn into adult plants. How do we model the dynamics of these three populations and their transitions? We have a transition of seeds in plants to seeds inside the animals that move and get deposited and become part of the substrate and eventually germinate. So this is the interactions that we are trying to model. So let us focus on the blue ones, the seeds that move, the moving seeds. Their source is ingestion. Ingestion by the animals. So the source of the seeds, of the blue seeds here, is ingestion by the animals. In principle, ingestion will depend on the density of animals, which are the ones that eat them, and of available seeds. And since essentially the seeds in this level are essentially animals moving, they are inside the animals, the dependence on U can be modeled as a typical logistic term, typical of population dynamics of animals. And the dependence on P, it can be just a parameter if there is enough availability of seeds in the plants, but there can be a kind of satiation also, like here. So it's linear for small population for small availability of seeds in plants, with a satiation if the animals have this kind of behavior, the animals that eat them. So this is the source. When the seeds are inside the animals, they move. So there will be some moving part in the description of the dynamics of the blue seeds in the animals. Let us put diffusion just to put something that we can model. So the equation turns from a differential equation to a partial differential equation. So it's diffusion equation now. And finally, those moving seeds get deposited somewhere at some later time. Which seeds are deposited? The ones that were ingested previously at an earlier time. So we can take account of them by integrating the ingestion of seeds and then the ingestion of seeds at different spaces and previous times, and then being transported by an appropriate kernel, which in this case will be the Gaussian kernel for the diffusive transport. So we integrate over all the positive ingestion points, and we have our deposition of ingested seeds. So the innocent equation of the beginning has now transformed into an integral differential equation, non-local in time, which is a very intimidating kind of beast. What will happen to their solutions? Okay, in particular, before the inclusion of the non-local term, the equation was the well-known Fisher's equation. In particular, if the ingestion, the dependence of ingestion on the seeds on plants is just a parameter, this is just Fisher's equation. This is a parabolic equation, not a wave equation, but because of a mathematical miracle that many of you may know, the solution, it has solutions in the form of traveling waves. They are front waves, like the one I plotted here, that move at a constant speed without changing shape. What will happen with the seed dispersal equation, which is slightly more complicated with this integral non-local term? Will it also have traveling wave solutions? At which speed will they move? So this is what we wonder. In the case of the Fisher equation, there is a simple argument that you may know. First, we do the traveling wave ansatz, which is this change of variables into a new variable that combines space and time. And in this variable, this new variable C will travel with the wave. So in this new variable, the traveling wave will be stationary, U of C, and its form, U of C, will be the shape of the traveling wave that I had in the previous slide. When you do the change of variable into the equation, it transforms into an ordinary equation in U of C, which I represent with primes. And this equation has a mechanical analog that the physicist can't avoid by seeing. Do you see it? If we rearrange the terms, U is the coordinate of a particle of mass d moving in a non-linear potential. So this is just Newton's equation with an acceleration of the particle and a nonlinear force. The force has two terms, the blue part, the ingestion part, which can be derived from a potential, and a viscous drag depending on the velocity u prime. And C, the velocity of the propagation of the waves, will be the viscosity in this mechanical analog. So the physicist can just interpret the solution of this equation as the motion of this particle in this nonlinear potential. The particle will be initially at the top of the hill of this potential at t minus at z, which is the time, minus infinity, which is the condition over there to the left, to infinity to the left. And it will have to move to the left in the potential, which is this motion here, and it will have to reach 0 at time plus infinity, which is c plus infinity over here. So the particle will have to move from here to here and stop here. And this will happen with a particular value of c, which will give you the velocity of the propagation of the waves. So it will have just the right viscosity to reach this point with 0 velocity at time plus infinity, right? This is the standard way of interpreting the solution of a traveling wave in Fisher's equation. What happens in the full non-local equation that I showed you? Again, say that ingestion is just the logistic. If the kernel, if diffusion or actually anything bell-shaped, what the integration does in that case, this kind of kernel extracts the value of this function, the ingestion function, where x prime is close to x, where x prime is equal x, and x is c plus c tau. Tau is the delay that you can see here, the non-local part. If this is narrow enough, we can even write this approximation. We approximate the integral as the value of the integrand function at the point where x is equal to x prime. So the integral part in the equation will be approximately this part. So you see, again, it has the logistic form. It's u times y minus u, but u evaluated at a different time. Instead of being evaluated at c, like this part here, it will be advanced in time. So this is the same force. This will be the same force as in Fisher's equation, but advanced in the value of the time c. So the situation will, and with a minus sign. So the situation will be almost the same. The particle at each time z, at each time c, would feel the same force as in the case of the Fisher equation, minus the value here, which is advanced in time, which is smaller. So it will feel a smaller force. Since the particle will feel a smaller force, it will need less friction to arrive at u equals 0 at time z equal infinity with 0 velocity. So the velocity, which is the viscosity, will be smaller, so there should be a slower wave. This is the kind of, this is the nice part. This is the real, the rule of thumb argument that I wanted to tell you. And this is what really happens. The problem is mathematically very complicated, and we made several approximations that I show you here, including a numerical solution of the integral differential and non-local in time equation, which is this red curve that shows the velocity of the front as a function of the time delay that the seeds pass inside the animals. And you can also see the two asymptotic values here. When tau goes to infinity, which gives you Fisher's equation. When tau goes to infinity, you can perform the calculation exactly, and it will give you this value of the velocity, and these are the slower waves. And when tau goes to 0, which is no animals, you can also do the calculation exactly in the integral and get this value. And you see that the numerical solution gives you precisely the intermediate values with these two asymptotic velocities. We also made several, two actually, analytic approaches to this problem, what that we called asymptotic, which is valid for small values of the decay, which is this red curve. The numerical in this case is the black one. And another one that we called iteration. Iteration is valid for all values of the time delay, and you see that it's very close to the numerical one, always with a larger value. So in between, we have this transition of the velocity between the two values that corresponds to Fisher's equations. The asymptotic method uses a formula, very old formula by Laplace for integrals of this type, which is valid in this region. And you can do it, and you get a characteristical transcendental equation from which you get the value of the velocity, as it's the standard way of doing it in the Fisher's equation. And the iteration method, we are thankful to a couple of guys that published an equation very similar to ours, from which you can also get a characteristic equation and a transcendental characteristic equation that gives you an analytical value of the inverse dependence of the speed on the delay, from which you can get the velocity as a function of the delay, which is the one that we show here. But those are technical details. The nice part was really trying to see if there would be waves and with what velocity of propagation. So for the expansion of the population, of the vegetation, the thing that I showed before was a simplified scenario with only one of the variables, with dynamics, the variable of the seeds propagating inside the animals, which is enough to see the main behavior. But of course, you should couple the variables, for example, the variable u that I showed you before, with the others. In particular, if you couple it with the p, the seeds in plants, the ingestion, this is so difficult word in English, ingestion variable, this provides a drive from P to U, and the loop closes with the third variable, which is S, because these seeds eventually become seeds in plants. If you consider that this one is instantaneous, so you ignore the time for germination, which is actually very fast, but actually this time is the time for the plant to grow and start producing seeds. So it's not just only germination. But anyway, if you just consider the germination, so this is instantaneous, you are left with two variables, and you have a second wave inside the wave of U that I showed you before, the slow front propagating at a constant speed. Inside that, behind it, there is a second wave of seeds in plants, of course, moving with the same speed. And that was the almost instantaneous part of the interactions. So that is a crude approximation, but the complete system is very complicated to get any analytical result. We ended up studying the full dynamics only numerically. I only want to add that we have not only calculated these things, we also moved ourselves into into the forest to actually track the movement of the animals with equipment designed and built by ourselves. And you see there the theoretical physicist in the forest. I was the only one carrying a chair because I'm old. The students sat on the ground. And there's something that I didn't mention at the beginning. These animals are nocturnal. So this was a very difficult effort because we had to measure this during the nights. During several nights, we stayed in the forest. If you never stayed in a forest at night with lights out, it's intimidating. Because you start hearing things moving around you, and you know there are predators, there are pumas, for example. So this was done in one of the municipal parks of Bariloche. It was very nice to do it. And the effort is still ongoing, and we are even moving to other animal systems. These are examples of the trajectories that we measured. The hammer? No, of course not. It's to defend yourself from the pumas. These are the trajectories that we measure. So thank you.
So we have questions here.
Thank you, Guillermo. Very nice. Can you describe briefly the equipment that you're using to track the animals?
Yes. This really didn't work. So I wouldn't advise anybody to do this. It was actually radio tracking. You see there is an antenna there. We attached a radio transmitter to the animal, to the back of the animal. This is completely another talk. And the transmitter emits pulses. And we get the pulses with the antennas and using several stations. Each station has 2 antennas. and we detect the phase, yes, the phase of the signal, the phase difference of the signals from 3 different points in the forest, and from that we trilaterate the position of the animals. But it's very difficult to do it because there are echoes and attenuation from the vegetation. Inside the forest, the GPS positioning does not work. So actually, we stopped doing this and we moved to open space. We chose an animal that is diurnal, moves in the open, and slower. Tortoises. So now we are attaching a heavy and larger. So we can attach to the back of the tortoises a complete set of behavioral tracking devices. They are not in Bariloche. Unfortunately, we have to travel to the coast, to San Antonio. I will tell you a little about that tomorrow.
But who implants all this stuff? I mean, the measuring stuff in the animals. So you collaborate with
the engineers in Centro Atómico Bariloche. Yes.
I see.
And one of the physicists in our group, which is now, she was a PhD student of mine during this time. This was her work, Laila. She has become the leader of this line of the research, and she is planning and doing everything. And we build the things ourselves.
And I wanted to ask you something. Could you compare the trajectories that you got with your model? Or
No.
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 Okay.
No, we
because
couldn't
you
do
had
that.
the trajectory of the animals, not
Yes.
the seed dispersal data.
Exactly.
So you are not following the seeds.
No, we wanted to do that. We talked with because our main collaborators were the zoologists in the ecology laboratory in another university. The data of plants are held by plant biologists or plant ecologists, and they are very jealous of their data.
Oh,
They
nice.
wanted to talk, but they didn't, because they know where every plant in the forest is, because they work here in the same park. The zoologists were very open, but not so the botanists.
I see. Are there any other?
Thank you for the talks. We have a very similar project in Rio de Janeiro with marsupials of the Mata Atlântica, and we have quite a lot of data of space displacement. The data there were collected using spool and line techniques.
Yeah, we also did that here.
Yeah, that
previously
works very well for small scales, and for large scales we also use telemetry. It's quite difficult. There is this kind of problems, particularly in Rio, because of the hills in the Serra. But if you work on large scales for the animals with which we work, like the delphins, on large scale of more than 1 day, 1 week, for example,
it gives you good data.
You
I can
obtain
imagine.
good data, and so, for example, you can explore this difference of scales.
Yeah, they are complementary. Like
Exactly.
spool and line. Spool and line is very good, but it doesn't have the time scale. You don't know how they cover the region.
You don't have the timestamps.
So you will always need these complementary techniques.
Yeah. And another technical question about the Fisher equation. The Fisher equation with local interaction without the time memory, like in your case, can generate a stationary solution with spatial patterns. Do you think that your equation...
With some boundary conditions?
Yeah, with the boundary condition. Do you think that your equation with these integral terms, which also has memory, can generate these special patterns or not?
I think so. That's very good. That's very interesting. Yeah, we haven't tried it, but it may be so. Yeah, okay.
Okay, thank you.
Let's talk later.
Okay. So I think we have one last, you're with the last one to ask, and then we go to the coffee.
Guillermo, thanks so much for the talk. Very interesting connection between different parts of physics and ecology and biology and everything. It's amazing. I work a lot with movement ecology, and it is a relationship between the movement, the ecology of the movement, and how the behavior of the movement of the animal and the outcoming dispersal kernel that you can obtain from that is very interesting. Do you think did you manage already to include some kind of complexity in the diffusive term there, to include like correlations in animal movement, etc.?
For the analytical results, we only use diffusion just because it's easy to work with. I don't know what will happen with other kernels. Numerically, it's very easy to put whatever you want. And you're right, probably diffusion is not the best choice for every animal. But I don't know. I don't know if you can do any analytical calculation with other kernels. Perhaps with some special ones, you could. Yes, you're right.
Okay, so thank Guillermo again. And so we now have the coffee break, and we come back at 11.